Welcome back. In this video, we're going to talk about our first example of generating lines using the description of vector value functions. We're going to focus on output in R2. In order to begin this discussion, let's do a quick recall. When we define the equation for a line, we start with 2 points. Let's call them P with the coordinates of P x1, y1, and Q x2, y2. Recall the word equation up and through this point has really meant scalar equation, and this has meant real valued. So we haven't really looked at vector valued equations yet, but we're going to do that by the end of this video. We have 2 points, and those 2 points allow us to calculate the slope of a line. This is a recall of your previous life. So we say that the slope is the rise over the run, which is the difference between the y values divided by the difference between the x values. And then, of course, we have many different forms that we can write these scalar equations for. So the first one, and my favorite, the one that I would get tattooed on my arm if I had to choose one of these equations, is the point slope form. And that looks like y minus y1 equals m plus x minus x1. In this case, I've just brought the y1 over to the other side. We can use this to transform our general equation in point slope form into slope intercept form, which is the famous y equal mx plus b. M is the same slope, and b is the y coordinate of the y-intercept. And then we can do a little bit of algebra to turn it back into standard form. That is a review of our knowledge of scalar equations for a line. Let's go ahead and use this review in practice. So suppose that we want to find the scalar equation for the line through the points P and Q given by 0, 2, 2, 3. We start by calculating the slope. And in this case, we say that the slope, m, would be -3 minus a -2 divided by 2 minus 0, which of course is -1/2. And then we can put this in point slope form. And maybe we choose point P to make it super easy. So this is y minus -2 equals -1/2 outside of x minus 0. And of course, this would be y equal to -1/2 plus 2. And of course, this plus would turn into a minus when I brought it over to the right-hand side. Okay, so now we have the scalar equation for this line, and it was a scalar equation because the y value, the output, was written as a single variable function of the input. So here, the scalar output is written as a function of the input right here. Let's see how we can use this to create a vector equation of a line. Well, the whole idea of a vector equation of a line was that we have these 2 vector valued outputs, which we called x of t and y of t. And you could also call this x comma y. The y value from our scalar equation was going to be equal to -1/2 x minus 2. We just did that calculation. Here we can actually break this into 2 pieces. We could break it into the piece involving the x scalar, and then we could break it into a constant vector. And notice that when I add 0 to x, I get back to x. So this is a kind of a placeholder. Here I'm breaking this off, and then all of a sudden we have this scalar vector multiplication where I'm factoring out an x, 0, -2. Notice this is not a function of t. Right now our parameter is x. And also notice that here when we have the direction vector 1, -1/2, there's a fraction there. I generally like to clear that fraction. In fact, if I let myself imagine that the slope of -1/2 means I go 2 over and 1 down. And notice there's a translation, kind of like a chain rule thing going on here. When x is 1, t would be 1/2, right? To get the same value out, we let t be equal to x divided by 2, or another way to say this is x is equal to 2t. And we can check that this works. When t is 2, the first coordinate here would be 4, and that would correspond with 4 times x. We see we now have a vector equation for the line given by t times v plus r naught. We're going to call v our direction vector, and then r is going to be some point on the line. And in our case, we know exactly what r is. It's this one. So this is going to be our direction vector v, and then this is going to be our point on the line, which we started with r naught. Let's go ahead and use Mathematica to graph both the scalar equation of the line and the vector equation of the line using parametric equations. Here we are in Mathematica. I have an open notebook, and I've already saved my notebook as lesson 5 examples. We're going to start by introducing a scalar valued function for our line. So I call this scalar valued function lowercase f. I use lower cases when I define the function. We use the brackets to indicate input, and then I put x with an underscore to represent that this is going to be a variable to be read into Mathematica rather than a constant scalar that's stored in memory. Here we use the assignment operator, delayed assignment, which is the colon equal sign, and that says, hey, listen, do not evaluate this immediately until told to do so. We say that the scalar equation was 1/2 x minus 2. I'm going to suppress that. I don't need to see that output. Now that I have that scalar equation, I'm going to want to plot it. The reason that I use plot is that this is an explicit function. It's not an implicit relation between the output and the input. It's an explicit one. And so we use the plot command as we discussed previously. Here I'm going to go ahead and plot f of x, and I'm going to do so over a range of x values. In this case, maybe I choose -6 to 6. And that's enough for my beginning plot command. So here's the output of that command, and maybe I need to zoom out just a little bit to make it easier to see the entire screen. All right. I can start to customize this command. I can turn the style of this plot to be a little thicker, so I'll use the directive. Here it is. And then we'll use the thickness. And then perhaps we call the thickness maybe 0.008. And you can play around with this. Here I'm going to go enter. So it just makes it a little bit thicker. Let's go ahead and test that the 2 points that we claimed are actually on this line. So here we've got p equal to 0, -2. I'll suppress that output, and we had q was equal to 2, -3. In order to do this, I'm going to use the show command. So I'm going to go ahead and do 2 different graphics in the same window. And to combine graphics in the same window, you can think about this as like copy paste. You're literally superimposing on one graphic another graphic. So here we go. I'm going to go ahead and do graphics. I open and close the brackets, and I want to do the points. Okay, so I open and close brackets, and then inside I'm going to put 2 points, P and Q. All right, kind of hard to see those. So here I'm going to do open bracket, close bracket, and that just says everything within those brackets I want to have in the same style. And I'm going to put point size 0.03. So that should make those points a little bit bigger. Oh, it's complaining because the bracket is not in the right position. Okay, so there's those 2 points that we claimed should be on there. We can further do some work here. Perhaps I want to control the ticks here. So one thing that I could do is I could write ticks. That means I'm going to control the ticks. And then I could do each tick mark separately. So let's say that I wanted only -1 and 1 on the x direction, and -2 and 2 in the y direction, right? I actually want to do something better than this. I'm going to go ahead and introduce a table. And I'm going to do the table that runs over all i's, where I goes from -6 to 6 in the x coordinate. And then the table in the y coordinate, I'm going to go from -6 to 4, right? And I want to just show you something real quick. This table literally just produces all I values between -6 and 6, where I is assumed to be a integer. So if I were to actually output this table, you see it? It produces all -6 to 6. And then I wanted to show you something else. If you ever have a question about a command and you just do double question mark and then type the command in and then evaluate that, Mathematica will come up with a list. This is from the Mathematica Documentation Center. And then if you click this double arrow right here, this will lead you to a very beautiful description of what that command does. And it also gives you some examples of how it works. This is what I like to say: if you teach someone to code, if you teach a mathematician to code, she can solve some problems. If you teach a mathematician to teach herself to code, she can solve all problems. So that's exactly what we're doing here. This is just a way to kind of figure out what the heck's going on by yourself if you need it. So the double question mark is quite a useful command. Okay, so we've just created the tick marks on this thing to be exactly what we want to do. And then maybe we want to control the plot range. So here we have plot range. And we're going to do the range in x and the range in y. Here we probably want the range in x to correlate with what we're doing in our plot. So we call that -6 to 6. And then perhaps we call the range in y -6 to 4. And I have to think about that for a bit. Or if you're really excited, maybe you call this -6 to 2. Okay. As we see, here is the plot that we wanted, and it was a combination of a plot command, a graphic command, and then some options on the plot. Next, what I'd like to do is redraw the same plot using our parametric equations. So here we're going to do something called parametric plot, and it's not in 3D, it's in 2D, so it's just called parametric plot. This is end the parametric plot command. All right, remember that we said that the y value here was going to be 2t plus 0, and then the x value, the x value was going to be 2t plus 0, and then the y value was going to be -t minus 2. And in this case, we're going to let t run from -6 to 4, or to 6. Oh, it's complaining because I didn't specify the t. Notice this is a different value, and that was because t was equal to x divided by 2. So really I should be saying 3 and 3. Okay, so now that almost looks like the exact same plot as above. What's going on here is that we are graphing each of the x and y coordinates together, and we're doing so by using the parameter t. So this is a parametric plot that allows us to graph the exact same line as we did above, but it does so parametrically rather than using scalar. We can still do the same type of options on this one. So here I can control the plot range. I could control ticks if I wanted to, so I could literally just do the exact same tick marks. I'm going to copy this code and put it here, and notice it has the exact same tick marks as we expected. We could also combine this with the points, but I think that gets you an introduction. The plot command is used for scalar functions. Graphics commands are used for graphic primitives, points, arrows, etc. And then the parametric plot command is used to graph vector-valued functions, or another way to say that is parametric equations. We'll see this more as we move on. In the next video, we'll continue our discussion
of vector valued functions.